So these are my email. I think that's okay. So I would be referring some of the things I may skip. I would be referring primarily BD quality for X-ray diffraction. It's a very good textbook on X-ray diffraction, elements of X-ray diffraction by BD quality, and I will also be referring to solid state physics, Ajay Ghatak, as and when it is needed, I mean displayed, I will just tell you. So when you talk about magnetic materials, just as I said, my magnetic materials may be an isotopic. So depending upon in which direction you apply magnetic field, magnetization may change. You can see the change in magnetization. So based on if the sample is getting magnetized easily, we call those directions as easy directions. If they are getting magnetized with difficulty, I would say by applying maximum or more amount of magnetic field, we call that direction as hard magnetic. So these are the issues that you can easily handle through this kind of tool or technique, how to identify the direction or the orientation. So I am going to talk about this very important topic. It is determination of crystal structure, study of crystal structure through X-ray diffraction. Very fundamentals I will talk about, and I will also take you to a little advanced version where how to index the X-ray data, that I will just discuss. So there are few things to it's a very simple example or exercise. कहीं पॉइंटर है किसी के पास? पॉइंटर है? पॉइंटर नहीं, कोई बात नहीं, था तो सही. So if you see this picture, what is this picture? In this picture, what I have, if you see this, I took one slit, it's a single slit, and just opposite to it we place some source of light, and I am saying it's a monochromatic source of light. Light is incident to this slit, and that is a screen. So ideally speaking, what I should observe at screen, something like this, because the light is passing through the screen, the slit, and the image of this you can see it here. So generally I would say I would see this kind of spot at screen, but actually depending upon certain things, what do I observe is something else. What is it? Something else. Is this. I can demonstrate this also. Instead having a bright spot just opposite to this slit, what do I observe? A bright spot, and then there is a dark region, and then there is a bright spot, again dark, bright, dark, bright. And you see the intensity of this bright spot, here it is too high, and then the intensity has reduced like anything, further it has been reduced, and that has been reduced gradually. So instead getting a bright spot, I do observe this kind of pattern, provided this has a number, this B has a number. What is that number B? If width of this slit is of the order of what? Wavelength of the incident light, then you can observe this kind of pattern. If B is too high, then perhaps you won't get this kind of thing. So to see this pattern, my primary condition is that wavelength of the incident light has to be comparable to what? Width of this light. So this will give you what? Very high intense peak, intense bright spot at here, and then you will have a pattern. So I think physics wise you all know this, but let me just mathematics, let me just show you. So what has been assumed as if this slit is made up of n number of equidistant points. कैसे कैसे सर? बहुत छोटे छोटे points हैं, and they are equidistant. Let's say the distance between two consecutive points is delta. So these points may act as a secondary source. So when light is coming to these points, they will behave as if secondary, they are the secondary source, and from there n number of wave will propagate, and when these L wave will propagate, they will superimpose, interference will occur. So based on these n number of waves, mathematically we have written these are the expressions for those n waves. They have a phase difference of phi. From where this phase difference is coming, sir? Between two waves. See, between this and this, there is a part difference of delta. Because of this part difference, there will be a phase difference. You know, what is the relation between phase difference and part difference? Phase difference is 2 pi by lambda into part difference. So just put the value of part difference, you will get the value of phi. And if you solve this, you will get intensity expression like this, where beta has a relation with the angle theta. So you see, this expression will give you information about the intensity that you see at the screen. If you see this, those who are, you see, let us look at this expression. If beta tends to 0, this beta, which is related to theta, theta is the angle of diffraction, how far you go from the center. So if beta tends to 0, this whole expression tends to 1, resulting intensity to be maximum. So when theta is equal to 0, when you are exactly opposite to the slit, intensity is too high. And when you, इसमें ये भी ऐड कर सकते हैं क्या हम, इसका ये कंट्रोल के लिए नहीं लगेगा है? If it works, देखते हैं आ जाए तो, नहीं कोई बात नहीं. And if beta is equal to m pi, provided m is not 0. If m goes to 0, beta goes to 0 and beta goes to 0, then this equation goes to maximum. So if beta is equal to what? M pi, or I think it was related to theta like this, beta is equal to b sin theta. That means b sin theta is equal to m lambda. M has values, कौन सी सारी integral values except 0. Then for these values of beta or b sin theta, if m is equal to 1, 2, 3, what will happen? This expression will give you what? 0 intensity. So whenever theta follows this relation, you get what? You get what? 0 intensity. 0 intensity means you get dark. So now if you see this, when you are exactly opposite to the slit, intensity is too high, which is I naught. When you go slightly away from that, you see some minima. That means when this condition is met, m is equal to plus minus 1. If m is equal to plus minus 2, you get another minima. In between these two, you get something else. What is that? To get further secondary maxima, it's a very trivial algebra. You take derivative of this intensity with respect to beta equated to 0, then this will give you condition where my further secondary maxima you can see. How to get secondary maxima? If you solve this, it is a equation, and from this equation beta is equal to 10 beta comes, and this equation cannot be solved trivially when algebraically. What you have to do, you have to plot two graphs, one for y is equal to beta, one for y is equal to 10 beta. So what is y is equal to beta? It is a straight line. What about y is equal to 10 beta? These are the curves, and wherever these two curves meet, you get solution. And solution, the first solution you get at 0. So at 0 you already have seen maxima. Second solution is at between pi and 2 pi. This is the position around somewhere around 1.45 pi. Third you get between 2 pi and 3 pi, which is 2.4 pi 2.46 pi, between 2 to 3. So at these values of beta, what you have got? You have got another maxima. So whenever condition for beta 0, this are met, you get maxima. Now let us check, okay, for this value of beta, what is the value of intensity? Just put the value of beta here and see what is the value of intensity. It is about 5% of what? The central one, I naught. So when you are at here, you have huge intensity, which is how much? 100%. When you are at this position, intensity has reduced to what? About 5%. When you are at here, intensity has further gone down to about 1%, I would say. So that's a typical spectrum theoretically you should be observing. So theoretically what would have been observed कि एक maxima होना चाहिए था, afterwards there would have been a minima, and then another maxima, then minima, maxima, minima. And if you see the experimentally observed data, it matches, right? So just when beta is equal to 0, you have huge intensity. When you go little away from here at this position, you see dark. So this is the position when beta is equal to pi. At pi it is 0. And when you are between pi and 2 pi at this position, Yes, there is an intensity, and this intensity is this, which is about 5% of the central intensity. So my experimental data can be theoretically explained. कब पहली कंडीशन हमने मानी, how we could explain this? We assumed as if this single slit is divided into n number of equidistant slits, और सब एक secondary phase difference एक दूसरे के साथ provide कर रही हैं, and that has resulted into this kind of pattern. ये single slit diffraction है. थोड़ा सा और आगे चलते हैं हम लोग. I have one, I'm just deliberately I'm discussing this. If I have instead single slit, I have got n number of slits. This is the case where you have got n number of slits. So first this single slit will give you diffraction. This another slit will also give you diffraction. This will also give you diffraction. So there are n number of single slits, right? And on those n number of slits, there is a light made incident. And if you mathematically check, then the mathematically expression for intensity comes out to be this. है ना? For this, you have an expression. What is that? I is equal to I naught sin square beta by beta square. For this also, for this also, for this also. But between this and this, there is a part difference or phase difference. What is that part difference? In terms of this theta. So basically, this is my expression for intensity. Here, my first term sin square beta by beta square, I am calling this term as diffraction term, or D term I call. Second term, it is sin square n alpha or n gamma by sin square gamma. कभी alpha कभी gamma book लिखती रहती है. This is my interference term, and beta has a relation with what? Please remember, this beta is related to slit width, and this gamma is related to slit separation. Center of this slit to the center of this slit. So beta is related to single slit width, or it is related to diffraction. Gamma is related to slit separation. It has something to do with the interference. Now if you see this, for these values of gamma, if gamma goes to what? M pi, you see, this is mathematics simple. If gamma goes to M pi, simple करेंगे तो 0 by 0 आता है, and to solve this, what you have to apply? L hospital बोलते हैं आप लोग, है ना? So you take derivative at numerator, derivative at denominator, then you again apply the same limit, you get this value n plus minus n. बहुत interesting, बहुत very fundamental I am talking about. By the way, what was capital N? Capital N, we choose number of slits, and I am saying that there are large number of slits. कितनी है? बहुत ज़्यादा है. मैं कहूँ कि let's say 10,000 number of slits per inch, मतलब 1 inch distance में कितने slits हैं सर? 10,000. So when gamma goes to m pi, this equation gives you intensity as n square times. So remember what is that? If n is equal to 10,000, then what will happen to the intensity? N square times I naught. So basically this intensity कब? When gamma is equal to m pi is huge. ये कब हो रहा है सर? जब ये सारी की सारी wave constructively interfere हो रही हैं. So since for these values of gamma, when gamma is equal to m pi, intensity become very high. This condition is, we call this condition as condition of principal maxima. We call it condition of principal maxima. शायद हम लोग डिफ्रैक्शन में इसी की बात कर रहे हैं. When I am saying gamma is equal to m pi, और gamma is related to what? Pi by lambda d sin theta. So मैंने क्या किया? गामा क्या रख दिया? m pi, है ना? So d sin theta become what? m lambda. रखो ना यहाँ पर. Let's place gamma is equal to m pi. Pi से pi cancel और d sin theta become m lambda. Here m can take any value. 0 से लेकर कोई वैल्यू ले सकता है ना? Right? So this is the condition of what? Getting what? कैसा मैक्सिमा सर? प्रिंसिपल मैक्सिमा मतलब intensity will be huge, है ना? And the values of m can be any integer, और मैं इस पे बहुत डिटेल नहीं करूंगा. So if you see this picture, it is the position where m is equal to 0. It is the position where m is equal to 1. This is the position where m is equal to 1. Essentially, if this term would not have been contributing, which one? Sin square beta by beta square, इसकी maximum value तो 1 है ना, उसके बाद तो gradually कम करता है. So this term will, what it will do, when you move away from the center, this term will gradually reduce down the intensity, है ना? So what is happening here? What is happening here? See, when you are coming away from the center, intensity is gradually going down. So this is n is equal to 0, m I would say, it is m is equal to 0, this m is equal to 1, 2 and so on and so forth. So these are the peaks having huge intensity. In between these two peaks we get some more intensities, and their intensity is comparatively low. You can study it from any book on optics, but their intensity is not very high. We call these maxima as secondary maxima. और दूसरा ध्यान दीजिएगा कि वापस से मैं फिर वापस पीछे आऊंगा, सॉरी, yes. By the way, what is this? This pi. It is the position of first what? Diffraction minima. किसका minima सर? It is the position of first diffraction. कब मिल रहा है सर? अच्छा, मिनिमा से मतलब क्या? इंटेंसिटी इज इक्वल टू 0, ठीक है ना? m इज इक्वल टू 0 मतलब मिनिमा, मिनिमा मतलब इंटेंसिटी 0 मतलब डार्क. सो डार्क मिनिमा 0 इज सेम थिंग. अच्छा, मान लीजिए इस पोजीशन पर, लेट्स से एट दिस पॉइंट डिफ्रैक्शन का मिनिमा आ रहा है. मिनिमा मतलब इंटेंसिटी 0. सपोज इसी पोजीशन पर इंटरफेरेंस का मैक्सिमा आ जाए तो क्या होगा? क्या होगा सर? हाँ जी बताइए. See, suppose there are two terms here. One is diffraction term, this is interference term. Suppose at some value of gamma, which is gamma is equal to m pi, this term gives you maxima. Which term? This term gives you maxima, matlab bright. But at the same value of theta, if this term gives you minima, minima matlab 0. So 0 multiplied by maximum will give you what? 0. So the resultant will be what? Kya? Minima. So though my interference is giving you maxima, but since at the same position diffraction term is giving you minima, so resultant will be what? Minima. अब ध्यान दीजिए, मैंने कहा मान लीजिए at this position let's say m is equal to 3 is there. M is equal to 3 means third interference maxima. So when I am saying m is equal to 3, I talk about थर्ड इंटरफेरेंस मैक्सिमा. कौन सा मैक्सिमा सर? प्रिंसिपल मैक्सिमा. द इंटेंसिटी बहुत ज्यादा है. सो व्हेन m इज इक्वल टू 3, it gives you third interference maxima. Which maxima? Principal maxima. So at this intensity is very high, but at the same value, at the same position, if this term gives you what? Minima. तो क्या होगा सर? Minima means 0 is multiplied by maxima, total gives you what? 0. तो क्या मिलेगा सर? 0. तो मुझे मिलना चाहिए था तीसरा क्या? थर्ड इंटरफेरेंस मैक्सिमम, बट आई एम नॉट गेटिंग थर्ड इंटरफेरेंस मैक्सिमम, रादर आई एम गेटिंग व्हाट? 0. आई एम गेटिंग dark. This is very famous what? Missing order. So what is happening at third order of interference principal maxima? Let's say first diffraction minima is falling. So what is happening as a result? My third order interference principal maxima is missing. फिर ध्यान दीजिए हमने क्या कहा? If for nth order principal interference maxima, if at the same position mth order diffraction minima falls, then what will happen? The corresponding nth order principal interference maxima will be absent. तो ये भी पिक्चर में देखिएगा, तो ये भी सिलेक्शन रूल में आएंगे सब. इंटर डिफ्रैक्शन में सब चीजें समझ में आती हैं. You see this picture. Basically this peak corresponds to 0. This is for 1 first interference maxima. This is second. Somewhere here would have been third. क्या हुआ? डिफ्रैक्शन का एनवेलप आया और यहाँ पे 0 गिर गया. सो व्हाट हैड हैपेंड? एट दिस पोजीशन वी वर एक्सपेक्टिंग थर्ड इंटरफेरेंस मैक्सिमा, बट एट द सेम पॉइंट व्हाट हैड हैपेंड? फर्स्ट डिफ्रैक्शन मैक्सिमा मिनिमा फॉल्ड, सो दिस वाज मिसिंग. सो दिस n इज इक्वल टू 1, 2 and third is out. So basically if you see the experimental data, experimental screen, what will happen? You will see these maxima. ये maxima कम दिखते हैं. Why? Because इनकी इंटेंसिटी इतनी है कि कई बार बैकग्राउंड नॉइज के आसपास होती है. सो इट इज़ वेरी डिफिकल्ट टू फिगर आउट वेदर दीज आर द मैक्सिमा और नॉइज. एक और आप लोग सब समझते हैं, बिटवीन टू प्रिंसिपल मैक्सिमा देर आर n-1 वॉट मिनिमा एंड n-2 सेकेंडरी मैक्सिमा. पढ़ा आप लोगों ने? सपोज 4 स्लिट का आपका सिस्टम है, तो देर विल बी 3 मिनिमा, n is equal to 4. So n-1 means 4 - 1 3. So here how many minima are there between two maxima? 1, 2, 3. So basically this is a result of what? N is equal to 4. इससे भी just by looking at graph you can tell how many slits are there. So already I have said n is equal to 4. So number of minima. अच्छा, just see one more thing. This minima, this minima, and this minima, these are the minima corresponding to interference. ये minima कौन से हैं सर? Interference के minima. और what is this minima जो यहाँ पर आकर गिर रहा था? It was diffraction minima. So between two principal interference maxima, there will be n-1 interference minima. कितने minima मिले मुझे? 1, 2, 3 because slit is 4. And between two principal interference maxima, there will be n-2 secondary maxima. कितने maxima दिख रहे हैं आपको? 4 minus 2 is 2, so it is 1 and 2. So there are two secondary maxima. Basically हम maxima में concern बहुत ज़्यादा नहीं because their intensity is not that very high. My interest is in these maxima. So what did I say till now? If you take a single slit, you get diffraction pattern. If you take what? N number of slit, you see this kind of pattern. Now in nature, if you look at the material, there are two types of materials. One is amorphous, one is crystalline. Crystalline means your atoms are arranged periodically. So one atom, after a certain distance, another atom. So these atoms are so nicely arranged, so systematically arranged कि it behaves as if it's a natural grating. एक nature ने आपको एक N slit दे दिया है. So I am showing you this kind of some real data where my atoms are arranged. See how nicely they are arranged. It's a TM picture, है ना? How nicely my atoms are arranged. See the discipline. देखिए जो हम लोग हैं और जो nature है बहुत अजीब है. Nature is so disciplined. कोई भी मैक्रोस्कोपिक से नीचे चले जाइए, so nicely. इसमें मैं थोड़ा भी चेंज करूंगा, प्रॉपर्टी बदल जाएगी. Any small change if I try to make, its property will change. So this is one. See the distance between these two layers is 2.34. It is throughout the system it is same. So this is my crystalline material. So in crystalline material my atoms are arranged periodically, that too over a long range, and because of that I can treat this crystalline material as a natural grating. Phenomena वही क्या कि you take grating, have a light incident on it and you look at the diffraction pattern. So diffraction pattern बहुत पुराना है. कितना पुराना है सर? ये 100 साल से ऊपर 125 के आसपास हो गया है सर. So this phenomena is very old. The only thing is, हाँ लगभग हो चुका है. The only thing is light is there. जो आपका ग्रेटिंग से हमने बात किया उसको रिप्लेस करना है किससे? किसी भी क्रिस्टलाइन मटेरियल से. बट द ओनली थिंग इज टू सी दोज डिफ्रैक्शन मैक्सिमा. व्हाट वाज द प्रिंसिपल रिक्वायरमेंट? व्हाट वाज दैट? मैं सिंगल स्लिट के लिए बोला था. व्हाट वाज दैट? द वेवलेंथ ऑफ इंसिडेंट लाइट शुड बी ऑफ द ऑर्डर ऑफ व्हाट? विड्थ ऑफ द स्लिट. तो मतलब देखो विड्थ ऑफ स्लिट कितनी दिख रही है आपको? सॉरी, ये स्लिट की विड्थ कितनी है? अराउंड 2 है ना. एक दो पिक्चर और देख लीजिए. See how nicely these atoms are arranged. See. So based on how my atoms are arranged, you know, there are 7 type of crystal structures, है ना. So primitive cell is my unit cell. ये सब आपने पढ़ा इसलिए मैं skip करूँगा. And you have lattice parameters. If it is cubic, A, B, C all will be same. If it is orthorhombic, then A, B, C will not be same. And depending upon how alpha, beta, gamma are related, if they are 90 degree all, then it is cubic or right. So based on the relation between A, B, C and alpha, beta, gamma, I have got 7 type of crystal structures, right. इस पर हम आ रहे हैं. So there are 7 type of crystal structure, and based on these relations, we have got 7 structures: cubic, tetragonal, and until triclinic. And for a given structure, how my atoms are arranged? If my atoms are sitting at corner alone, then it is simple. If they are sitting in addition to corner, if they are sitting at the center of face, it is face centered, and then maybe base centered. So based on how my atoms are sitting, you have further classification, or we call them Bravais lattices. In cubic there are 3 Bravais lattices: simple, body centered, face centered. And for orthorhombic we have simple, body centered, face centered, and base centered. And then you have 14 type of Bravais lattices. So every crystalline material can be placed in these 7 type of crystal systems and 14 type of Bravais lattices. इस पर थोड़ा और बात करूंगा मैं, 1-2 मिनट ले रहा हूँ, ज़्यादा नहीं ले रहा हूँ. Very simple. If you take a simple cubic, if it's a closed packed structure, my atoms are sitting at corner. If it is a body center, in addition to what? Corner, you have a atom sitting at the body center, and so is with FCC. And you also know this Miller indices. Based on how my atoms are arranged, you have planes, right? And to designate these planes, you need some numbers. We call these numbers as Miller indices. You take 3 integers, place it in small bracket. We call this system as this arrangement as Miller indices. कल बात कर रहे थे, बहुत ज़्यादा चूँकि सब लोग पढ़े हुए हैं इसलिए बहुत नहीं बात कर रहा हूँ. So here, if you see, if this is x, this is y, this is z, then this is my 100 plane. This is my 1. If this is x, this is y, this is z. This is my 110. This is my 11 plane, and then you can create these planes. सब आप लोग करते रह रहे हैं. Okay. Here I am showing you the planes. This corresponds to 111. This corresponds to 100. So you can actually see these planes through TEM. You can actually see these planes. I was just telling this plane, and then you have directions. So it is the direction which is defined between, it is line between 2 points, origin and the end point, right? So, and these directions are defined by similar numbers, but you place them in square bracket. Now, if you see this picture, very interesting, I have just discussed it. You take, let's say, case of iron. You take a case of iron. In case of iron, if you apply magnetic field along 100, what is 100? Along x direction, then what will happen? It will saturate easily. It will magnetize easily. So when field is applied along 100, it is getting saturated by very small amount of applied field. But if you apply magnetic field along this body diagonal direction 111, then saturation is, I think, 4 times higher magnetic field. So here for iron, 100 is said to be what? Easy direction. 111 is said to be hard direction. So I can design, I can develop, I can create, I can engineer a material as per my own wish. If I could synthesize iron having direction along 100, if he has synthesized iron with 111 orientation, then for me I will say it can be easily magnetized. For him it cannot be easily magnetized, right? So these are the things, and this is another thing. I just said planes, HKL. So the distance between 2 successive plane, we call this distance as interplanar spacing, and that's how this interplanar spacing D is related to what? Lattice parameter. If it is a case of cubic this, rectangular this, and hexagonal, किसी छात्र ने शायद एक problem solve किया, so you are aware of this. So if you see this formula, just see this formula. This formula, here there are 3 variables. पहला D, दूसरा A, third is HKL. So here A is what? A is the lattice parameter. The very fundamental property of any crystalline material is A. If I ask you to find out what is the lattice parameter of any crystalline material, what you must have? You must have D, you must have HKL. So getting D is simple. कि पहले आप plane देख लीजिए, उनके बीच की distance निकाल लीजिए. But the problem is how to find out HKL. Issue is, if you want to find out A, you must know D, but to get D, you must know which HKL you are talking about. So we will just combine all the thing, है ना? So this particular relation will help me in finding out or estimating very fundamental property of any crystalline material, which is my lattice parameter, and I call it A. Okay, so now we have checked diffraction and some very fundamentals of crystal structure. For diffraction, what is needed? Wavelength of incident light has to be of the order of what? Slit width. For crystalline material, the distance between 2 successive atoms is almost of the same order. क्या है? 2, 3 what? Strong. So if you wish to see diffraction pattern through these crystalline material, what should be the typical order of wavelength? It should be almost of the same number. So if you see this electromagnetic radiation स्पेक्ट्रम ऑफ इलेक्ट्रोमैग्नेटिक रेडिएशन, इसमें देखिए ये मेरे पास ये फ्रीक्वेंसी है, वेवलेंथ रेंज है, राइट. सो इन 1 to 2 एंगस्ट्रॉम विच रेडिएशन कम्स, देखिए हियर दिस इज एक्सरे. एक्सरे हैज वेवलेंथ बिटवीन 1 to 100 एंगस्ट्रॉम. एक्सरेज हैव वेवलेंथ बिटवीन 1 to 100. बाकी आप ऊपर नीचे चले जाइए, इसके पहले इससे ज्यादा अल्ट्रावायलेट, यूवीएन है ना. सो दैट यू नो. So to study crystal structure of these crystalline material, you would be requiring what? Some light. Which light? That has wavelength comparable to what? Slit width or these lattice parameters. So we choose what? X-ray. अब problem क्या है? Problem कुछ बड़ी है. कुछ चीजें किताब में शायद नहीं होती हैं, मैं शायद कुछ बात करूंगा. When we talk about X-ray, मैंने शुरू में बोला था एक शब्द मोनोक्रोमेटिक वेवलेंथ. मोनोक्रोमेटिक वेवलेंथ मीन्स दैट इंसिडेंट लाइट शुड हैव जस्ट वन वेवलेंथ. और मैंने यहाँ कहा 1 एंगस्ट्रॉम से लेके लगभग 100 एंगस्ट्रॉम इज एक्सरे. सो टू स्टडी टू सी द डिफ्रैक्शन पैटर्न यू मस्ट हैव एक्सरे ऑफ वन वेवलेंथ. लेकिन देखते हैं होता क्या है. इफ यू ट्राई टू क्रिएट एक्सरे, हाउ एक्सरे इज क्रिएटेड? यू टेक ए ट्यूब ले लीजिए, है ना, ठीक है. इस इन दो एक फिलामेंट है, ये मान लीजिए आपके पास टारगेट है कॉपर, यहाँ पर इलेक्ट्रॉन्स है. इफ यू अप्लाई पोटेंशियल बिटवीन दीज टू, व्हाट विल हैपन? दीज इलेक्ट्रॉन्स विल हिट टू दिस टारगेट, ये डीएक्सेलेट होंगे, एंड एज अ रिजल्ट व्हाट विल हैपन? सम रेडिएशन कम्स आउट, एंड दिस रेडिएशन वी कॉल एज एक्सरेज, है ना. दैट्स हाउ इट्स ए टिपिकल एक्सरे ट्यूब. ये मेरे सिस्टम के अंदर हियर इज अ ट्यूब, इट्स टिपिकल एक्सरे ट्यूब. हाँ चलिए थोड़ा अब एक वर्चुअल एक्सपेरिमेंट करते हैं हम लोग. इट इज माई ट्यूब, एक्सरे ट्यूब. हियर वी हैव कॉपर टारगेट and then we are applying positive potential to this copper and negative here. There are electrons in between. If you apply voltage, what will happen? Electrons will move from here to what? Target, and accordingly what will happen? X-rays will emit. So let us apply some voltage and try to study. यहाँ जो एक्सरेज आ रही हैं इसको किसी डिटेक्टर में पकड़ लीजिए, है ना. Store it in detector and try to see how wavelength and intensity follows. Let us apply very, I would say 5 kilovolt of what? Potential. Here you have applied 5 kilovolt of potential. How the intensity will look like? यहाँ से आएगी और थोड़ा बढ़ेगी, फिर वापस से डिक्रीज होनी चली जाएगी. If you see this spectrum, it has wavelength starting from where? 2.4 to 2.4 onwards. So this radiation has how many wavelength? It has wavelength starting from where? 2.4 angstrom onwards. अब क्या किया मैंने? Let us increase that potential to 10. What had happened? ये मेरा जो पॉइंट यहाँ से शिफ्ट होके यहाँ पे आ गया, and what had happened? Intensity has gone up, फिर बढ़ी और फिर वापस से चली गई. So corresponding to this 10 kilovolt, what had happened? X-ray has wavelength starting from let's say 1.2 angstrom onwards. फिर एक काम करते हैं, फिर बढ़ा लेते हैं. Similar kind of pattern I do observe, और बढ़ा लीजिए. तो ये जो तीनों मैंने स्पेक्ट्रम देखा है, in all these spectrum, the kind of wavelength that we are getting is continuous. क्या है सर? मुझे wavelength एक पॉइंट onwards लगातार मिल रही है. Since I am getting continuous wavelength or I am getting all wavelengths, we call this radiation as what? Continuous X-rays or white X-rays. White मतलब it has all mixed wavelengths. So this radiation is my what? White X-rays or continuous X-rays. मैंने पहले कहा कि मुझे वो X-ray चाहिए जिसकी एक wavelength हो. So for me these X-rays are of no use. For me these three X-rays are of no use because it has these X-rays have all possible wavelengths, right? फिर हम चेंज करते हैं ये. Let us increase it to what? 25 kilovolt. Similar pattern, but we suddenly see two peaks. एक छोटा peak और एक peak यहाँ पर दिखता है. So this peak is corresponding to let's say 0.6 or 0.7 kind of wavelength. इसको थोड़ा और बढ़ाइए तो what will happen? You will see similar kind of pattern, but you will see this peak at the same position. Peak मिलता रहेगा, उसकी intensity बढ़ती चली जाएगी. So this peak position will remain same. कब? If you apply potential more than 25 kilovolt. So if we keep increasing this potential, position of this peak, the intensity will increase, but the position will remain same. So इसकी position कब बदलेगी sir? When the position of this peak will change? The moment I replace this, जो मैंने यहाँ पे target लगाया है, अभी मैंने टंगस्टन लिखा है, टंगस्टन हटा के कॉपर लगा दीजिए. The moment I replace this target, what will happen? Position of this peak will change. So basically this position of this peak is a characteristics to what? To the target. And we call this radiation as characteristics radiation because it is a characteristics to what? Target material. थोड़ा physics और बात कर लेते हैं इसकी. So this is my characteristics radiation. बाकी सब क्या है सब है? White radiation. अब समस्या क्या है? I don't need white radiation. मुझे क्या चाहिए? मुझे वो एक्सरे चाहिए जिसकी केवल एक वेवलेंथ हो. तो इसमें से काम करता हूं मैं, somehow let me suppress all this. ये 4 के नीचे जितना भी मेरे पास रेडिएशन है उसको क्या कर देता हूं मैं? Let me just filter it. Let me just suppress it somehow. है ना? और फिल्टर करने का तरीका क्या है? इसके आगे कुछ रख दीजिए, है ना? वो एब्जॉर्ब करेगा वो. या तो ये होगा कि सारा एक्सरे एब्जॉर्ब हो जाएगा, है ना? मैं इस तरह का फिल्टर चूज करता हूं कि only this much is suppressed and this small kink is left. छोटा kink बचता है. And this kink has a wavelength of what? Let's say here it is 0.6 angstrom. So now for me that small kink that has a one wavelength is important. तो मुझे करना क्या है? To study crystal structure I need X-ray. Which X-ray? That has only one wavelength. क्या किया मैंने? पहले X-ray प्रोड्यूस किया, फिर मैंने उसके आगे कुछ रख दिया, so that my unwanted X-rays are stopped or it is absorbed. Only the required or needed X-ray is coming out. That needed X-ray is my characteristics X-ray. So I hope you know what is characteristics X-ray. कैसे X-ray emit होती है? जब आप इस इलेक्ट्रॉन को यहाँ से नॉकआउट करते हैं, what happens? The electron next to this K shell, it comes from here to, sorry, this is KL. So the electron from L jumps to K. What happens? Wavelength corresponding to what? Corresponding to what? The energy level between these two emits out. तो ये characteristics किसकी है सर? Target की. So this is my that peak I am talking about. So you will get a peak corresponding to this, and I am interested in that. This is my characteristics X-ray. So if my X-rays are emitted when the electron is jumping from here to here and here to here, we call them K alpha 1, K alpha 2. If it is coming from M to K, it is K beta. ध्यान दीजिए, if I am saying K alpha 1, K alpha 2, see K alpha 1, K alpha 2, I have shown the intensity ratio is 10 to 5, means half. So K alpha 2 has an intensity half of what? Intensity of K alpha 1. और ध्यान दीजिएगा, since the energy difference between these two is very small, so what will happen? The wavelength coming out, wavelength of this K alpha 1 and K alpha 2 will be very close. Whereas wavelength of K alpha 1 with K alpha, K beta might be little far. तो मेरे पास किस तरह के स्पेक्ट्रम आ रहे हैं सर? किस तरह के पीक आएंगे? Let us say this is K alpha 1. It has intensity half. This is, let's say, K alpha 2. This is K beta. So K alpha 1, K alpha 2 are very close. Why they are very close? Because these levels are very close, right? So K alpha 1, K alpha 2, and this is K beta. Since K beta is very far, it is easy for me to filter this K beta out. इसको तो मैं easily बाहर पकड़ के फेंक सकता हूँ. Whereas if you want to filter this K alpha 1, K alpha 2, then it might be tricky. अभी मैंने बताया आपको कि K alpha 1, K alpha 2, the intensity ratio is 1 to 2.5, है ना? If I am trying to filter K alpha 2 somehow, if I am trying to filter, मान लीजिए दो हैं, ये मान लीजिए K alpha, ये मान लीजिए K beta है, sorry, K alpha 1, K alpha 2. Its intensity is what? 50% of this. If I am trying to filter this out, I need to filter this, right? So I will be compromising with what? Intensity of K alpha 1. If I try to filter K alpha 2, I would be compromising with the intensity of K alpha 1. So if, unless and until it is needed, I don't think it is going to create any problem to you, because these wavelengths are very close. So for bulk, I think, for bulk or for polycrystalline, X-ray having K alpha 1 and K alpha 2 is okay. So majority of X-ray diffractometer, they have K alpha 1 and K alpha 2 by default. K beta फिल्टर कर लेते हैं, बट दोज हु आर वर्किंग विथ थिन फिल्म्स, वेयर द epitaxial thin film, where the lattice parameter of film and substrate are very close, then it will be almost impossible for you to find out whether the peak are because of k alpha 1 or k alpha 2 or it is because of film or substrate. So in that case it is compulsory for us to filter out what k alpha 2. जो लोग कहते हैं सर thin film attachment लगा दी, उनका मतलब क्या है सर? They are trying to filter this k alpha 2. Okay, so my one purpose is solved. This is, let's say, इसमें हमने filter कर लिया है. That's how my k alpha 1 and k alpha 2 are. If you try to filter this k alpha 2, what will happen? Intensity कितनी बचेगी सर? मैंने इसको filter कर दिया, half बचती है, right? So if I try to filter anything, I am basically compromising with the intensity. एक बहुत simple rule है, exams में आता रहता है. To filter this out, let us place a filtering sheet. We call it absorber. और उसका एब्जॉर्प्शन किस तरह से, वील जस्ट सी टू इट, इस पर हम बात नहीं कर रहे हैं अभी. सो दिस एब्जॉर्बिंग प्लेट एक्ट्स एज ए फिल्टर, और एक बड़ा अच्छा रूल है कि फॉर दीज टारगेट्स दीज आर माई फिल्टर मटेरियल. हम लोग कहते हैं यू टेक एनी एटॉमिक नंबर जिसका टारगेट है, उससे एक एटॉमिक नंबर कम फिल्टर होता है. सो इफ यू कॉमनली वी यूज कॉपर एज ए टारगेट एंड करस्पॉन्डिंग टू कॉपर निकल इज एक्टिंग एज ए फिल्टर. तो देखिए क्या हो रहा है, मान लीजिए जो मैं डॉटेड लाइन है, दे आर माई एब्जॉर्प्शन, दिस इज माई एब्जॉर्प्शन स्पेक्ट्रा, डॉटेड लाइन, एंड दिस इज माई एक्सरे स्पेक्ट्रा. सो इफ यू पुट दिस absorbing material, what will happen? This k beta will be out, this will be out, and I will leave with what? Only this much peak. So if you are using copper as a target, nickel will act as a filter, and I will have just one wavelength coming out to me. So these are the typical wavelengths that we use. For copper it is 1.546, है ना, हमने 2 डिजिट तक लिखा है. So okay, so let us summarize until here. To study crystal structure of crystalline material, the phenomena that we are going to use is diffraction. And to see the diffraction, what is needed? I need X-rays. क्यों एक्सरे चाहिए? बिकॉज ऑफ द लेटिस पैरामीटर. कौन सा एक्सरे चाहिए सर? कैरेक्टरिस्टिक्स एक्सरे, नॉट वाइट. उसको रखने के लिए आई हैव जस्ट शोन दीज आर द थिंग्स. सो दिस इज वेरी इंपॉर्टेंट इंफॉर्मेशन कि आई नो डिफ्रैक्शन फिनोमेना, आई नो द एक्सरेज, आई नो हाउ टू गेट एक्सरेज. द ओनली थिंग इज क्लब बोथ ऑफ देम एंड सी व्हाट बेस्ट वी कैन गेट आउट ऑफ इट. सो दैट कुड बी विजुअलाइज बाई जर्मन फिजिसिस्ट ब्रैग एंड ब्रैग, आप सब लोग इसको जानते हैं. सो दिस वाज स्टडीड बाय दिस फादर एंड सन पेयर, ब्रैग एंड ब्रैग, जर्मन फिजिसिस्ट. बहुत सिंपल है, इस पर तुम फिर ध्यान दीजिएगा, मैंने कुछ पहले बताया है उसको ध्यान दीजिएगा. लेट अप, ये सवाल मैं पूछता रहता हूँ और ये इंटरव्यू में बहुत पूछते हैं हम लोग. सिलेक्शन कमेटी में बहुत पूछा जाता है, पीएचडी में आगे भी ध्यान दीजिएगा. सपोज देयर इज अ लाइट कमिंग, दीज आर द एटम सिटिंग, देयर इज अ लाइट कमिंग इन, एक्सरे, लाइट मीन्स एक्सरे कमिंग इन, इट इज कमिंग एंड मीटिंग एट दिस पॉइंट ए, इट इज गेटिंग व्हाट? इट इज गेटिंग, मैंने लिखा है रिफ्लेक्टेड रे. देयर इज वन मोर लाइट रे विच इज कमिंग इन एंड इट इज बीइंग रिफ्लेक्टेड फ्रॉम हियर. सो बिटवीन दिस रे एंड दिस रे व्हाट इज हैपनिंग? दिस रे इज ट्रेवलिंग सम एडिशनल पाथ. कौन सा पाथ? BC and CD. So this second ray has traveled some distance extra as compared to this ray. What is that path? BC plus CD. Or in terms of known parameters, I would say this is a known parameter D. It becomes what? 2D sin theta. So basically, this ray has traveled how much distance extra? 2D sin theta extra as compared to beam number 1. So that means there is a physical path difference between these two rays. And if my path difference is integral multiple of what? Wavelength, then I would be getting which condition? कौन सी condition थी सर? Condition of getting principal interference maxima, जहाँ पर intensity बहुत ज़्यादा आ रही थी. So if this condition gets met, कौन सी condition? If this 2D sin theta is equal to what? Integral wavelength of wavelength किसका? जो incident light है. I would be getting huge intensities. आप क्या करिए, एक सैंपल ऐसे रख लीजिए, यहाँ से एक्सरे पास कीजिए, यहाँ डिटेक्टर लगा दीजिए, डिटेक्टर को रोटेट कीजिए यहाँ से, है ना, डिटेक्टर रोटेट करेगा, जैसे ही ये थीटा कंडीशन मिलेगी, क्या मिलेगा मुझे, पी क्यू मिलेगा, इंटेंसिटी बहुत ज़्यादा, क्यों होगी इंटेंसिटी बहुत ज़्यादा, कंडीशन ऑफ प्रिंसिपल इंटरफेरेंस मैक्सिमम गॉट सेटिस्फाइड। अच्छा, ये सवाल हम लोग पूछते रहते हैं, फिर पूछ रहे हैं, मैंने लिखा है रिफ्लेक्टेड रेज, एंड हियर you see, can I say, although it is known as Bragg's diffraction law or law of diffraction, but instead Bragg's law of diffraction, can I say Bragg's law of reflection? Why I am calling it law of diffraction, not law of reflection? Yes, anyone, what are the laws of reflection? Tell me. हाँ बताइए, laws of reflection क्या है? Okay, so angle of incidence is same as angle of, so first condition is set. Second, are they in same plane? हम ड्रॉ कर पा रहे हैं, they are in same plane, और हो गया, तो why I cannot say it X-ray reflection, why I am calling it X-ray diffraction? मैंने शुरू में शुरुआत किया था, I started with Snell's law, कुछ उस तरह से बात करूंगा। हाँ जी, can I say X-ray reflection? मैंने बताया सवाल में इंटरव्यू बहुत पूछते हैं, हाँ है ना, यहाँ पर सेम है ना, नहीं वो मैडम रिफ्रैक्शन का केस है, इट इज रिफ्रैक्शन, हियर इट इज रिफ्लेक्शन, इट इज ए रिफ्लेक्शन, मैंने लिखा है यहाँ पर डिलिबरेटली, दिस इज रिटन एज रिफ्लेक्टेड, डिफ्रैक्टेड नहीं लिखा है, इट इज रिटन एज रिफ्लेक्टेड रे, एंगल ऑफ इंसिडेंस सेम एज एंगल ऑफ रिफ्लेक्शन, इंसिडेंट रे रिफ्लेक्टेड एंड नॉर्मल दे आर इन सेम प्लेन, सो फॉर मी इट इज ए रिफ्लेक्शन। अरे हम इतना क्यों आगे जाना चाहते हैं, अभी तो मैंने रिफ्लेक्शन ही पढ़ा है। हाँ, नहीं 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 नहीं, लॉ ऑफ रिफ्लेक्शन डजंट से दैट, मैं लॉ ऑफ रिफ्लेक्शन पे ही वही अटका हुआ हूँ। लॉ ऑफ रिफ्लेक्शन अब कुछ पार्टली सही कह पा रहे हैं, अभी मैं इसको करेक्ट करूंगा, पार्टली कुछ सही कहा आपने, लेकिन अभी कंप्लीट मुझे आंसर नहीं मिल रहा है। सॉरी, एनीवन हु कैन आंसर टू इट, व्हाई आई एम कॉलिंग इट एक्स-रे डिफ्रैक्शन नॉट रिफ्लेक्शन? एक बीच में आप लोगों ने एक बात छोड़ दी, लेट अस सी टू इट। तब भी वो तब भी मेरे पास लॉ ऑफ रिफ्लेक्शन तब भी फॉलो हो रहा है मैडम, रिफ्लेक्शन तब भी चल रहा है, एंगल ऑफ इंसिडेंस इवन फॉर दिस रे आल्सो, दिस थीटा एंड दिस थीटा इज ऑलवेज सेम। मैं थोड़ा सा करेक्शन कर दूं, आई थिंक यू विल एग्री टू इट। see let me just make a small correction to what he has said. Law of reflection is true for every angle of incidence, है ना? कितने एंगल ऑफ इंसिडेंस हो सकते हैं? इनफाइनाइट। You take any angle of incidence, there will be corresponding angle of reflection, है ना? But यहाँ जो मैं बात कर रहा हूँ, क्या कर रहा हूँ? This condition is not getting satisfied for every angle of incidence. किसके लिए हो रही है सर वो? For certain or limited value of angle of incidences, this condition, कौन सी condition? कि जब दोनों का path difference कितना हो रहा है? It is equal to integral multiple of wavelength. So it is not reflection, it is diffraction. This phenomena is not occurring at every angle of incidence, rather it is occurring at कौन से एंगल हैं जहां पर ये कंडीशन सेटिस्फाई हो रही है. सो दिस इज नॉट डिफ्रैक्शन, इट इज रिफ्लेक्शन. अच्छा, एक और मैं आपको बता दूं, ये मैं दो तीन सवाल हम लोग बहुत पूछते हैं, मैंने आप इंटरव्यू में जाएंगे मिल जाएगा. ये एन क्या है? व्हाट इज एन? व्हाट डू यू मीन बाय ऑर्डर? अभी देखो बड़ा अच्छा आंसर आएगा. एन क्या होता है? व्हाट इज एन? ऑर्डर से मतलब क्या आपका सर? वन टू थ्री फोर ना, बट what do you mean by it physically? what is the meaning of it? ऑर्डर से मतलब क्या है सर? हाँ प्लीज. मतलब क्या है इसका? फर्स्ट सेकंड समझ में आ रहा है, बट what do you mean by that? How you feel about it? दूसरी लेयर से आ रहा है, मतलब 1 मतलब पहली लेयर से, 2 मतलब सेकेंड लेयर से, ऐसा कुछ है, ऐसी कुछ है. If you take one more layer, then it will be n is equal to 3. Am I right? अच्छा समझिए जरा, what is this 2d sin theta? It depends on d and theta, right? So आपने क्या किया, यहां से डिटेक्टर उठाना शुरू किया. You started increasing angle of theta, है ना, from here. So what had happened? 2 is a number, d is a number, and sin theta is a number. If you take multiplication of 3, you will get some number. If you start increasing theta, there will be some value of theta for which this whole quantity will come for the first time equal to what? Lambda. पहली बार क्या मिलेगा वो? पहली बार this for some value of theta, let's say theta is equal to 10 degree, this whole quantity will give you what? The whole quantity as a whole will give you value which is equal to what? Wavelength 1.54. So let's say for theta is equal to 10 degree, if this quantity is giving you 1.54, then I will call that particular condition as first diffraction minima, oh sorry maxima. फिर मैंने थीटा बढ़ाना शुरू किया, अब की बार क्या हो सर, थीटा इज इक्वल टू 20 डिग्री पर क्या हुआ, थीटा 20, 2d and sin 20, it gives you what? 2 into 1.54. Then at that theta, whatever maxima you get, what is that? अभी यार याद कीजिए, भी मैंने थोड़ी देर पहले इंटरफेरेंस एंसलिट का मैक्सिमा बताए थे. n इज इक्वल टू 1 क्या था, 0 के बाद 1 गया, कब, जब n इज इक्वल टू 1, फिर 2, फिर 3, और इंटेंसिटी कैसे गिर रही थी ना. सो व्हेन n इज इक्वल टू 1, इंटेंसिटी विल बी वेरी हाई, n इज इक्वल टू इंटेंसिटी विल बी. अच्छा, यूनिवर्सिटी कॉलेज में आप लोगों ने स्पेक्ट्रोमीटर का एक्सपेरिमेंट किया होगा. ग्रेटिंग में कलर मिलता है हम लोगों को ना, प्रिज्म लगाते हैं, ग्रेटिंग लगाते हैं, वी सी द स्पेक्ट्रोमीटर. तो पहले मुझे कलर मिलता है, एक पैटर्न दिखता है ना, डबलेट दिखते हैं हम लोग येलो का. तो पहली बार मुझे कलर दिखते हैं, वॉयलेट, इंडिगो, ब्लू, ग्रीन, वो है फर्स्ट ऑर्डर. फिर थोड़ा स्पेक्ट्रोमीटर घुमाइए थोड़ा सा और, तो क्या मिलेगा, दोबारा से फिर मुझे वही पैटर्न मिलेगा, बट देयर इंटेंसिटी विल बी टू लो, दैट इज माय सेकंड ऑर्डर. सेम चीज है, वाला कुछ नहीं है. तो ऑर्डर हैज नथिंग टू डू विद व्हाट, नंबर ऑफ लेयर्स. लेयर से कोई मतलब नहीं है सर, है ना. सो दैट्स ए वेरी इंपॉर्टेंट थिंग. अब थोड़ा सा एक बात और देखिए, बहुत बेसिक बात किया मैंने. हाँ, so this is the typical experimental arrangement. This is the sample, where that's the sample holder. Here you mount sample with a source of X-ray, so X-ray comes at here, and from there it is getting diffracted. You have a detector, so it rotates by theta degree, है ना. Or whenever this condition of Bragg's law gets satisfied, you get lot many X-rays coming to detector, you see the maxima. So what you do is you record theta versus intensity, है ना, और मिलेगा कि आपको पीक मिलेंगे, है ना. अब जरा एक बात और करते हैं, वैसे ही पूछता हूँ आप लोगों से. मान लीजिए ये कमरा है, इस कमरे में इंस्टेड ऑफ सो मेनी टाइल्स आई हैव गॉट जस्ट वन टाइल. वन टाइल मीन्स देयर इज वन पर्टिकुलर ओरिएंटेशन, कोई एक ओरिएंटेशन है. इसका मतलब उन दो पैरेलल प्लेन्स के बीच में जो डिस्टेंस है सब जगह सेम है. कोई के नंबर ले लीजिए, राइट. सो इट हैज जस्ट वन ओरिएंटेशन. नाउ इफ एक्सरे इज इंसिडेंट टू इट, डी की वैल्यू फिक्स है ना, पूरे रूम में एक ही डी है ना. सो इफ यू ट्राई टू सी द एक्सपेरिमेंट, थीटा आएगी तो क्या मिलना चाहिए मुझे, एक्सपेरिमेंट में क्या दिखना चाहिए मुझे. इफ आई एम लुकिंग एट जस्ट फर्स्ट ऑर्डर, व्हाट काइंड ऑफ डेटा आई शुड ऑब्जर्व. यदि मैं थीटा वर्सेस इंटेंसिटी प्लॉट करूंगा, व्हाट डू आई सी, क्या मिलना चाहिए, पैटर्न में क्या दिखना चाहिए. I2 का सैंपल, एक सैंपल लिया जिसमें केवल एक ओरिएंटेशन है, राइट. X-ray is incident and I am talking about first order diffraction is equal to 1. So what do I observe if I plot theta versus theta x, intensity y? What do I observe? X-ray आई, हाँ, जिस भी d वैल्यू के लिए कंडीशन सेटिस्फाई हुई, क्या मिलेगा मुझे, एक पीक मिलेगा. अब थीटा बढ़ाते रहिए, मैं सेकंड थर्ड की बात ही नहीं कर रहा हूँ. सो फॉर एवरी वैल्यू ऑफ एंगल ऑफ इंसिडेंस मैं केवल फर्स्ट ही कंसिडर करना चाहता हूँ. क्या मिलेगा मुझे, आई विल ऑब्जर्व व्हाट, पीक. एक कितना पीक मिलेगा, 1 2 4 5 6 कितने, आई विल गेट ओनली वन पीक. इफ आई कंसीडर सेकंड थर्ड ऑर्डर, आई विल बी गेटिंग मोर नंबर ऑफ पीक्स, बट देयर इंटेंसिटी विल ग्रेजुअली गो डाउन. अब एक और तरीका ढूंढ लेते हैं हम लोग. 10 अलग अलग टाइल्स लगाते हैं, एक कुछ और ओरिएंटेशन की, जहां डी वैल्यू कुछ है, दूसरी where d value is something else, third with different d value, fourth with some other d value. Now you have X-ray. So for let's say for this plane, if my Bragg's condition is getting satisfied at 10 degree, so what will happen? At 10 degree I will get peak. Again you start increasing theta. ये तो खत्म हो गया. अब बराबर वाले जो plane है, let's say for that plane, once again my Bragg's condition got satisfied. Let's say it is at theta is equal to 30 degree. So at 30 degree I'll get one more peak. So you'll get what? Another peaks, right? If you have 5 similar kind of orientations, similar five different type of planes, then I would be observing how many planes? 5 planes. 5 plane means more than one plane. More than one means poly. So we call those materials as polycrystalline, है ना? अच्छा, if there is no oriented plane available, crystalline material है ही नहीं, तो क्या मिलेगा? क्या मिलेगा? Bragg's condition satisfy नहीं होगी, मिलेगा क्या? मुझे background noise मिलेगा. So if let's say I am a layman, जैसे हम लोग एक्सरे डॉक्टर के पास जाते हैं, ECG लेके जाते हैं, पता नहीं क्या लिखा रहता है, ऐसे हमारे पास एक्सरे भी लेके आते हैं. अब तो बहुत एडवांस हो, शुरू में जो शुरू कर रहे थे तो बड़ा मुश्किल था, क्या लिया है हमारे पास. So if let's say I have a material sample and X-ray has been done, so just by looking at X-ray, the very first information that you can have is whether the material is crystalline or amorphous. कैसे पता चलेगा सर? If it has a peak, sharp peak, it is crystalline, otherwise amorphous. If it has just one peak, that means it has only one orientation. If it has more than one peak, that means sample is polycrystalline. ये ठीक है? ठीक, इतना हमें मिल रहा है. तो इस पूरे एक्सपेरिमेंट में what do I get? थीटा वैल्यू और एक पीक. क्या मिल रहा है सर? थीटा वैल्यू और पीक. What is available with this Bragg's law? What is available to this Bragg's law? What is D? What is lambda? Lambda is the wavelength of incident light. वो फिक्स है. कहाँ से आ रही है? एक्सरे सोर्स से. What is D? It is also fixed. सैंपल के साथ है. What is variable? थीटा, है ना? तो from this experiment, if theta is known, lambda is known, you can find out D. If D is known, then I think you can remember the relation for cubic D is equal to A by square root H square plus K square plus L square. If you could somehow know HKL, you can find out lattice parameter. So to study lattice parameter, your next job is कि वो जो प्लेन आ रहे हैं वो प्लेन किस जो पीक्स दिख रहे हैं, दे आर फ्रॉम विच ओरिएंटेशन. अभी मुझे क्या मिला सर? एक्सरे किया तो मुझे क्या मिला? आई गॉट पीक्स, आई गॉट थीटा. सो विद दिस थीटा लैम्डा इज अवेलेबल. डी निकालना है आपको, डी मिल जाएगा. लेकिन डी कब मिलेगा सर? 5 पीक है तो 5 डी मिल जाएंगे आपके पास, 5 डी मिल जाएंगे. लेकिन वो डी किस प्लेन के हैं कैसे पता चलेगा? अनलेस यू नो कि दीज peaks are from this plane, तो मेरे लिए बेकार है. ठीक है सर? Now my next job is to find out what address of these planes, है ना? HKL. How to get HKL? ये थोड़ा सा ट्रिकी है, 10 मिनट और मैं बात करूंगा. ये मैंने बता दिया है. This is the XRD that we have with us in CIR. Same वो भी मैं दिखा रहा था. Sample holder, X-ray source, detector. मैं एम्फेसाइज कर देता हूँ आपको इस बात पे. एक्सरेज आर नॉट गुड फॉर ह्यूमन बींग्स, है ना? एक्सपोजर टू एक्सरेज. अच्छा, एक्सरे छोड़ दीजिए, कोई भी रेडिएशन हम के लिए हमारे लिए अच्छा नहीं है. एक्सपोजर टू एक्सरे इज नॉट गुड फॉर ह्यूमन बींग. तो बहुत पहले जब व्हेन वी स्टार्टेड आवर PhD, आवर रिसर्च, दैट टाइम दिस एक्सरे वाज इन ओपन. सो बड़ा टेंशन होती थी हम लोगों को, लेड की शीट डाल के एक दूर ऑपरेटर रहता था. तो बट उसके बाद से चीज़ें बदली हैं. So basically this whole experimental setup or X-ray setup is enclosed in this box. जो box है ना, ये box it is of iron, और ये सामने दिख रहे हैं glass हैं. So they are not the ordinary iron and ordinary glass. They have lead into it. It is lead added to it. So lead absorbs the X-rays. तो यहाँ पर एक light लगी रहती है ऊपर. So unless this is in this situation, you cannot switch on the X-ray. इसको बंद करना जरूरी है. बंद करेंगे इसका मतलब यू आर प्रोटेक्टिंग योर सेल्फ थ्रू फ्रॉम द एक्सरेज, जस्ट एज ए सेफ्टी. वैसे मैं पर्सनली आपको बताऊं, आई हैव बीन ट्रेन्ड लाइक दैट. दोज हु आर वर्किंग विद एक्सपेरिमेंट्स, प्लीज बी वेरी केयरफुल, वेदर इन केमिस्ट्री और फिजिक्स और इन एनीथिंग. दोज हु आर वर्किंग विद एक्सपेरिमेंट, प्लीज बी वेरी वेरी केयरफुल. उसमें कोई एक्सक्यूज नहीं है. जो केमिस्ट्री में है ना, लाइक एक बीकर से दूसरा मिला दो, नहीं भाई मत मिलाइए. पहले चेक कीजिए व्हेन यू ऐड A to B, कहीं ऐसा नहीं बम बना रहे हैं आप. है ना, फट गया, कुछ भी हो सकता है सर. So is with any experiment that you are dealing, please look at its safety things. देखिए रिसर्च तो बहुत सेकेंडरी है, योर लाइफ इज वेरी इंपॉर्टेंट, है ना, वेरी वेरी इंपॉर्टेंट. सो कभी भी एक्सपेरिमेंट हमें तो आपको बताएं कि जब हम कुछ एक्सपेरिमेंट करते थे, माई बॉस यूज टू सिट कि जब तक एक्सपेरिमेंट करेंगे आई विल बी सिटिंग विद यू. अकेले एक्सपेरिमेंट मत कीजिए, दो रहिए, है ना, एक को बिठा के रखने, चाय पिला देना उसको, बिठा के रखिए पास, वही बैठा रहे. इन केस ऑफ इमरजेंसी ही कैन हेल्प यू आउट. प्लीज फॉलो दीज. यदि आप देख रहे हैं इलेक्ट्रिक इंस्ट्रूमेंट में तो थोड़ा सेफ्टी को देखिए, कुछ भी तार मत पकड़ लीजिए, है ना. तो ये चीज़ों को, दे आर वेरी सिंपल थिंग, बट प्लीज. अच्छा, इंडिया में क्या है कि ह्यूमन लाइफ की बहुत ज़्यादा वैल्यू, सॉरी लाइव चल रहा है ना. बट या आई मीन पीपल डोंट केयर, 2 मर गए 10 मर गए, पीपल हार्डली केयर्स. बट इफ यू हैपन टू बी इन यूरोप और इन एनी डेवलप्ड कंट्री, देयर एवरी लाइफ इज इंपॉर्टेंट. सो दे विल बी वेरी वेरी पर्टिकुलर. ह्यूमन बींग और एनवायरमेंट के लिए हम क्या है कि यार एसिड लिया, काम कर दिया, उठा के नाली में फेंक दिया. We usually do that, but no, in Western world it is not the case. There is a proper disposing of mechanism. Unless you follow that protocol, no, you will be banned. जहाँ जरूरत है ग्लव्स पहनिए. हम लोग क्या है केमिकल यूज कर रहे हैं, पता नहीं क्या एस्टोन पी रहे हैं, केमिकल 4N प्योरिटी के कोई ऑक्साइड लेता है, खा गए पी. So though it is very common, acetone, working with acetone is very common, right? Everybody is working with acetone, alcohol. एक तो मेरी लैब में था यहीं पर, वो I won't name him, he is now faculty at IIT. वो अमोनिया खोल के एक्सपेरिमेंट कर रहा है NH4OH. मैं भाग के आया, मेरा बराबर में ऑफिसर में, क्या करा भाई? कुछ नहीं सर, बंद कर दूंगा. मैंने मर जाएगा, मुझे मारे खुद भी मरेगा, है ना. अमोनिया क्या करती है सर? क्या करती है अमोनिया, है ना, ऑक्सीजन खा जाती है. आप पता नहीं चले, अब गए, निपट गए आप. तो यू डोंट नो, NH4OH इसलिए खोल के मिला रहे हैं आप आस पास से, आप वहां खड़े भी यहाँ बड़े आराम से, थोड़ी देर में ऑक्सीजन गायब और आप गए, पता ही नहीं चला, मर गए. सुना है ना आपने जो ये आप क्या बोलते हैं, आलू के जहां भंडारण किया जाता है, कोल्ड स्टोरेज, न्यूज आती है ना कि वहां अमोनिया का रिसाव हो गया, 10 आदमी मूर्छित हो गए, मर गए, यही कारण है. तो वी हैंडल दीज थिंग्स विदाउट एनी केयर, बट यू हैव टू बी वेरी केयरफुल अबाउट इट. सो एक्सपेरिमेंट में ध्यान रखिए प्लीज. थ्योरी में इतना नहीं, बट एक्सपेरिमेंट में यू हैव टू बी वेरी केयरफुल. और बताता हूँ, एक्सपेरिमेंट में नहीं, हमारे यहाँ काम करते रहते हैं, 4 मंजिल पर चढ़ा है, कोई सेफ्टी नहीं है, कुछ नहीं है, क्योंकि फर्क नहीं पड़ता है. लेकिन उनके पेरेंट्स को, घर को तो फर्क पड़ता है ना, भले ही किसी को ना फर्क पड़े, बट जो है उनकी फैमिली को जरूर फर्क पड़ता है. हम लोग बहुत कैजुअल है, बताए ना, तार निकल रहा है, खड़े बैठे हैं, चाहे काहे तार निकल, देखते हैं क्या है, है ना. तो प्लीज बी, ये मेरे लिए एक पीस ऑफ एडवाइस है, प्लीज टेक इट विद यू. डोंट परफॉर्म एनी एक्सपेरिमेंट अनलेस यू हैव गॉन थ्रू इट सेफ्टी एडवाइजरी. प्लीज फॉलो दैट रिलीजियसली, इट इज फॉर यू. एनवायरमेंट को भी सेफ रखिए. हम तो वही है ना, डालते जा रहे हैं ना, एसिड लिया, ड्रेन में बहा दिया, बट यू डोंट नो व्हाट काइंड ऑफ कॉन्सिक्वेंसेस इट हैज. सॉरी, जस्ट डेविएटेड बिट. ओके, ये सब ठीक है. अभी समस्या मैंने क्या बताया, ये थोड़ा इंटरेस्टिंग पार्ट है, कुछ किताबों में है, कहीं नहीं है, थोड़ा इसको ध्यान दीजिएगा. आई सेड दिस इज द फॉर्मूला. क्यूबिक की बात करते हैं. इफ यू वांट टू फाइंड आउट ए, you should have D, you also should have HKL. So D you can find out. कैसे? Through those peaks. मिल गया? Now the only thing is how to get HKL. And for getting HKL, इसको जरा थोड़ा सा देखिए, values रख दिए मैंने. तो if you see this, for a given system, what will happen? Lambda is fixed, wavelength of incident light. A for a given system is fixed. 4 is constant. So can I say H square plus K square plus S square is proportional to what? Sin square theta, है ना. ये बड़ा इंपॉर्टेंट रिलेशन है. यू हैव थीटा वैल्यूज, यू हैव थीटा वैल्यूज. कौन सी थीटा? जहां पर मुझे पीक मिल रहे हैं. फाइंड आउट देयर साइन थीटा वैल्यूज, फाइंड आउट देयर स्क्वायर्स, राइट. मिल गया साइन स्क्वायर थीटा. अब उनका रेशो लेना शुरू कर दीजिए, जो कांस्टेंट है कट जाएगा, राइट. सो फ्रॉम द रेशोज ऑफ साइन स्क्वायर थीटा यू कैन फाइंड आउट रेशोज ऑफ व्हाट? H square plus K square plus. ये आपको मदद करेगा किसमें? For indexing these peaks. Very interesting thing. Simple है. थोड़ा देखते हैं इसको. Suppose I was just telling this, suppose you have got a polycrystalline system. Let's say for this particular plane crystal, my Bragg's condition got satisfied at 20, you will get a peak at 20. If it is satisfied at this, you will get another peak, and that's how you will be getting peaks. थोड़ी सी जानकारी और दे रहा हूँ. You have got three things here. One, you are getting peaks at different theta values. So these theta values will give you D, and this D will give you A. So position of these peaks will directly give you value of lattice parameter. There is one more thing, intensity of this peak. So here this peak is more intense, this peak is very less intense. So the intensity also tells you something. Intensity means what? What does that intensity mean? कि जहाँ पर intensity ज़्यादा, it means corresponding to that plane volume उसका ज़्यादा था. So that will give you कि 100, the volume of 100 crystalline plane was more. This will say कि no, this volume was less. एक और चीज़ें हैं, width of this peak, broadening of the peak. So if peak is getting broadened, that means my X-ray is getting diffracted from the smaller particles. So it will tell you information about particle size. इसमें debate है, although कुछ papers कहते हैं कि particle size is calculated from this peak width, but absolutely बहुत मुश्किल है ना. Qualitative analysis you can do. Qualitative means you take a sample and have it at different temperatures, then you get the XRD. So at various temperatures, if your peak is gradually widening, then you will say or it is getting sharper, you can say as the temperature goes, particle size increases. So that you can make, but absolute number is sometimes difficult. कुछ लोग question करते हैं इस पे. Okay. Now the issue is how to take this h square plus k square plus l square. एक समस्या है. For getting these numbers, कुछ rules and negative rules, we call them selection rules, and they are depending on one very important parameter. मैं उस पर डिटेल नहीं यार, हम लोग पढ़ाते रहते हैं. I hope you can try that. But when X-rays are coming, you have scattering from electron, you have scattering from atom, you have scattering from unit cell, and this will give you one parameter we call that parameter as structure factor. Sorry, we call it structure factor, and that's how we define this structure factor. It is the amplitude of wave scattered by all the atoms in a unit cell, and it is the amplitude of wave scattered by one electron. So this expression will tell you which planes are permitted and which planes are not permitted for a plane, for a system. This is a very important discussion. इस पर थोड़ा बात कर लेते हैं. एक केस लेते हैं हम लोग, simple cube. In simple cube, what had happened? My atoms are sitting at corners. So position of, let's say this is origin, so my atoms are sitting at where? 0, 0. अच्छा, इस origin को यहाँ से shift कर दूँ तब भी 0, 0. This is the expression for structure factor. If it is positive, you will get intensity. If it is not positive, you won't get the intensity. So this will tell you which planes are permitted. So in simple cube, you put x is equal to 0, y is equal to 0, you get, for every thing you will get what? These are few relations हम लोग use करते रहते हैं for calculating this. So if you take simple cubic case, you take any position, this as 0, so x becomes 0, y becomes 0, z becomes 0, it becomes e to the power 0, e to the power 0 means 1, and you have got value of a structure factor. That means you take any value of HKL. You take any value of HKL, क्या मिलेगा सर? फर्क नहीं पड़ता ना, HKL क्या है? If you take any value of HKL, you will get a value of structure factor. That means all reflections for simple cube is permitted. एक और देखते हैं हम लोग. It is a case of base centered. ले लीजिए आप लोग. In base centered, you have one atom sitting at here, one atom at corner. So this is sitting at the center of base. If this is origin, so one location is what? 0, 0, 0. What is the position of this? Half lattice parameter along x, half lattice parameter along y. So x is what? 1 by 2, y is also 1 by 2. So for these two, what is the structure factor f? This is for the origin atom, this is for base centered. If you solve, you get this expression. अब यहाँ ध्यान दीजिएगा, here expression involves h plus k. अब depending upon k what is the sum of h plus k, you will have a value of structure factor. क्या क्या permitted value हो सकती है सर? If h plus k is even मतलब दोनों मिला के, then what will happen? This will give you real value. और कौन कौन सा possible है? बोलिए, 0 is considered to be even. So if I say 0, 0, 1, so this is even, even is again even, 0, 0, 1 is possible. So is this. If it is odd, then situation is this. एक और देखते हैं हम लोग जरा. Body centered. अभी मैं इसको summarize करूंगा. If you see the body centered, this is the body centered. Position of this atom is what? 0, 0, 0. Position of this is what? Half lattice parameter along x, half along y, half along z, right? So for corner 1, this is the position, this is for the body centered. So I am getting structure factor relation like this. So depending upon now this relation, it will tell whether these particular planes are permitted or these planes are not permitted. किस पर depend कर रहा है sir? It is depending on sum of what? H plus k plus L, and if this H plus k plus L is even, you get positive, otherwise no. So only these planes are permitted, these planes are not permitted. ठीक है? So is with I think face centered. ये relation आएंगे face centered के लिए. Okay, मैं जरा summarize कर लूँ. So suppose you have simple cubic Bravais lattices. All reflections are permitted. Base centered, this is permitted for body centered. This is permitted for face centered. These are permitted. और एक मिनट. So if you see this, यदि हम लोग h स्क्वायर प्लस k स्क्वायर प्लस l स्क्वायर का जो नंबर है ना, इस नंबर को देखें, if I am getting these numbers as 1, 2, 3, 4 this, then it is the simple cubic. If I am getting these numbers as 2, 4, 6, 8, that means it is body centered. If it is 3, 4, 8, then it is a, है ना, इसी से निकाल के लेके आ रहे हैं हम लोग. अब जरा मैं क्या बोलना चाह रहा हूँ देखिए रहा. Suppose I have a simple cubic system. So these are the planes permitted. 1, 0, 0, h1, k0, l0. So h square plus k square l become 1. 1, 1, 0, it becomes 2, 1, 1, 1, it becomes 3, 2, 0, 0, 4. So these are the numbers, right? So if you are getting a 1, 2, 3, 4, 5, 6, 7, 7 is not permitted because combination is not available. If you are getting 1, 2, 3, 4, 5, 6, 8, 9, then you will say a system is what? Simple cubic. If you are getting what? मैंने बताया ना आपको अभी इसके पहले. Let's see this. If it is 2, 4, 6, 8, it is body centered. If it is 3, 4, 8, it is face centered. These are the, let's say if you are getting, you have FC structure, पहला P कौन सा मिलना चाहिए सर आपको? 1, 1, 1. 1, 1 means h square plus k square l is equal to 3, 2, 0, 0, 4, then 8, something like that. So is with BCC. अभी समस्या क्या आई मेरे पास? You have got value of h square plus k square l square. मिल गया आपको? इसका रेशोज मिलता चला जाएगा. थोड़ा इसको लोग एक एक्सरसाइज कर लेते हैं हम लोग. Suppose I took one sample and this is the XRD data that I am getting. I am getting 5 peaks available. These are the 5 peaks and these are the positions of 5 peaks. So 2 theta is available. So how to get these peaks indexed? क्या करिए आप? Firstly, you find out theta, then sin theta, then sin square theta. तो sin square theta values are this. अब क्या करेंगे आप? इनकी वैल्यूज को रेशोज लेना है. सो दिस इसको इसी के साथ लेना है. सो रेशो बिकम्स 1, 3.99, 7.99, दिस. तो इसको यदि आप इंडेक्स के टर्म में बात करेंगे तो इसकी कॉमन से मल्टीप्लाई कर, दिस बिकम्स 3, दिस बिकम्स 4, 8 एंड. सो पहला पीक जो मिला 38 पर वो क्या था सर? इट हैज अ रेशो ऑफ हाउ मच? 3. Second peak that was observed at 44.76, it has a ratio of 4. This has a ratio of 8. So this is basically which kind of structure I am talking about? FCC. So the first peak which we have observed at 38.52, it is corresponding to what? 111. The second peak that I observed at 44.76, it was 200. So I can index all these peaks. So I got the value of HKL. So for these positions I got value of HKL. HKL मिल गया. इस थीटा से D निकाल लीजिए. D आपके पास है. Formula you have. So for every peak you find out value of lattice parameter. इसको statistically average निकाल लीजिए, error निकाल लीजिए, you'll get the value of lattice parameter. अच्छा, if you start doing this for every system, it is a very complicated. अभी तो क्यूबिक बताया मैंने, टेट्रागोनल, ऑर्थोगोनल, बहुत मुश्किल है. So पहले हम लोग ये कर रहे थे, बट अभी क्या किया, सारे एक्स-रे डेटा को कंबाइन करके सॉफ्टवेयर में हम लोगों ने उपलब्ध कराया हुआ है. सो दैट सॉफ्टवेयर डज ऑल दिस. उस पर थोड़ा बात कर लेता हूँ. This is one more Scherer formula. If you know the theta, you can find out particle size. It's a very simple formula. Now, to index these peaks, I suggested this method. It was a manual method, but it is not possible these days to do it manually. बहुत मुश्किल होता है. So, आजकल database है, that is a very well-known ICDD database, International Center for Diffraction Data. पहले इसको JCPDS बोलते थे. It's a software, expensive software है. So I'll just show you quickly. That's how you see the ICDD file. तो इसमें ये 4 कॉलम है, file, PDF number, search. So if you know the file number, just put it here and you will get the data. So I'm just showing you. So if you, let's say if you know the file number, here example is 46 point something, just put it here, you will get this kind of data. So here you are getting D value and these planes. There is a provision of data conversion. This data conversion will convert into 2 theta. So you have got 2 theta values and positions of the HKL value. So you look at your own data, match it with these theta values, and then you can index के सर this peak correspond to 100, this correspond to 101. ध्यान रखिएगा, intensity is also important. If your own sample, यदि उसकी intensity इस position पर भी maximum और ये second maximum, तो you can easily say that this is your 101, this is your 100. Or if you don't know the file number, then you can select possible combinations through this elements, select element only, and this is a periodic table. From there you can choose the elements and you can get the value of JCPDS data file. Let's say if I am selecting silicon, so these are the, इसमें थोड़ा सा ध्यान रखिएगा कि these are systems, you have to check which system you are trying for, cubic, hexagonal, tetragonal, please be. एक थोड़ा सा मैं वैसे बता देता हूँ, यहाँ पर ये जो एक value आती है ना D, which there are a number of files in that data set, which you are supposed to take, यहाँ लिखा है calculated. I would recommend कि you use diffracted file. Calculated diffracted हो तो that is more authentic. So yes, that's how we do. I think I have a meeting after that. I'll just close it. एक छोटा सा मैं आपको बता दूं. What is this? It's a XRD of thin film. मैं आपको बताना चाह रहा था particularly. Here you see there are 2 peaks which are very close to each other. It is basically GGG is a substrate, and on top of it we have deposited TBIG. So it is a epitaxially grown film. I have a substrate of same crystal structure as that of my film. So if that kind of growth is there, then I won't observe any other peak. Substrate मिलेगा और film मिलेगा. So here I am getting a very sharp peak of substrate, and then there is a corresponding peak at peak of film. Please see, these 2 peaks are very close. If I use ordinary X-ray, then it will be very difficult for me to see this film peak. What do I be getting? I may be getting peak from K alpha 1 to K alpha 2. So in that case, I am supposed to filter that K alpha 2 out. So if you are getting this kind of structure, you can say that my film is epitaxial. And it is a typical of single crystal. अभी मैंने बताया था, if you have a single crystal, then you would be getting this kind of peak. या फिर ध्यान दीजिएगा, single silicon single crystal I am taking. If it is single crystal, I am getting 2 peaks. ये 2 peak कहाँ से आ रहे हैं सर? है ना? This is K alpha 1, this is K alpha 2. ठीक है ना? और वैसे भी पता समझ में आता है कि इसकी intensity is almost half. If you want to see just 1 peak, what you are supposed to do? आपको इस k-alpha 2 को भी हटाना है. So this is the peak after filtering k-alpha 2. Intensity will go down like anything. देखो कुछ 12,000 यहाँ बचती है, कुछ 6,000 के आसपास बच जाती है. Yes, this is again XRD of one single crystal, silica single crystal. So with this I will stop. I wish to acknowledge all the students and my mentors. These are my students, and I am thankful to my institute, funding agencies, DST, CSIR, TCube, and MNIT for providing so many things to me. Thank you. I am open for discussion. At certain slides I was very fast. I thought कि आप लोगों को पता है, कुछ नहीं भी पता है तो I am here. I will be discussing it. I also wish to extend one thing. We have X-ray diffractometer with us. If anyone is interested in using that facility, you are open, provided you have to follow some procedure. Otherwise, that facility is available. Okay, we will take you to a CIR. आज भी अभी भी जा सकते हैं. I think अभी नहीं tutorial लेंगे सर थोड़ा सा. So we have got relatively good number of facilities. We have got XRD, we have got VSM, we have got FESEM, we have got UV, visual, PL, FTIR. FTIR is about to come. और क्या है? Ellipsometer और TGA, sputtering, PLD, thermal coating, particle size analyzer, 4 probe station. TEM नहीं है. TEM is very expensive. I am not getting it through. Recently we have got FESE with EDX. So if anyone is interested, I would be happy to extend that facility. Yes. Any question that you wish to ask? It was a very elementary topic. अच्छा, मैंने इसको suddenly बीच में मुझे कहा गया पढ़ा दीजिए. See, whether it's a magnetic material, it is thin film, single crystal, whatever you do, you have to ultimately start with XRD. For every material scientist, the very first experimentation is XRD. So you must know how that XRD works. I have discussed so many topics. Those are very, very important, and they are important from the selection of interview point of view. बहुत पूछे जाते हैं. So please be careful about them. Yes, please. K is a correction factor. कोई ना constant है. 0.9 के आसपास आता है, करेक्शन फैक्टर है. मैं उस पर मैंने एम्फसाइज नहीं किया. कोई नंबर ले लीजिए, वैसे 1 मान लीजिए. चलिए मैं आपको k is equal to 1, इट्स अ नंबर. k मैंने 1 कर लिया है. 1 बेसिकली दिस शेरर फॉर्मूला मैं जैसे बताऊं आपको, ऐसे ही बता रहा हूं. अब इसको अभी चलने दीजिए. सपोज आई हैव 100 प्लेन है ना, एक पार्टिकल है दैट हैज अ ओरिएंटेशन ऑफ 100 और ऐसे 10-20 पार्टिकल एक साथ आ गए हैं. So what X-ray will give you? It will give you information. It will give you just one peak. तो 10-12 पार्टिकल का एक पीक दिखेगा. So for you it would be difficult to find out वो पार्टिकल साइज एक पार्टिकल का है या कलेक्शन ऑफ पार्टिकल्स का है. So that is why it is difficult. मतलब इसको बहुत ऑथेंटिक बोलते नहीं है. एक क्वालिटेटिव, I said qualitative analysis you can always do if you are performing experiment with just one sample. टेम्परेचर में अलग-अलग टेम्परेचर रख रहे हैं या कूल डाउन कुछ और कर रहे हैं. So qualitative you can always say कि by changing temperature particle size increasing or it is decreasing. So that statement you can easily make. But if you precisely wish to say कि sir my particle size is 10 nanometer, some of the experimentalists they accept, sometimes they say no we don't accept that. But it's a debatable question रहता है इस पे कुछ. So best way is to see the TM image. So in TM you can actually see this particle and you can measure it physically. So that's the best way of, and yes, because at that particle you you take the electron beam and check the diffraction pattern. So that way you can easily find out. So TM is the best way to tell you the particle size. Yes, and TM is also X-ray diffraction. Same. जो है वही ब्रैक्स कंडीशन है. सेम, इट्स अ सेम ब्रैक्स कंडीशन. एक्सरे में सैंपल हॉरिजॉन्टल है, टीएम में सैंपल एक्सरे में ऐसे है और रिफ्लेक्शन होता है. टीएम में इलेक्ट्रॉन बीम गेट्स ट्रांसमिटेड. और वेरी गुड थिंग अबाउट एक्सआरडी के सैंपल रिमेन सेम, इसमें कोई नुकसान नहीं होता. बट टीएम में सैंपल गोज नहीं बिकॉज यू हैव टू प्रिपेयर द सैंपल सो दैट इलेक्ट्रॉन बीम कैन ट्रांसमिट थ्रू. So thickness is very, मान ली if you are working with thin film, either you have to peel it off or you have to etch it so that electron beam can transmit through. सो इट्स अ डिस्ट्रक्टिव टेक्निक. दूसरा सैंपल साइज वेरी इंपॉर्टेंट इन टीएम. जो ग्रिड होती है बहुत छोटी होती है, 3 mm by 3 mm होती है. सो इन टीएम दैट इज़ वेरी इंपॉर्टेंट. इट्स अ टोटली डिस्ट्रक्टिव टेक्निक बट इट्स वेरी इंपॉर्टेंट, वेरी पावरफुल, महंगी भी है. Yes, anything? I will be here after some time. I have a meeting actually, so I will go right now and we may discuss all these issues in coming classes. ठीक है? कोई any question that you wish to ask? Quick question I can take. Yes, please. हाँ. नहीं नहीं नहीं, assume नहीं करना पड़ेगा सर. आपके पास तो ये जैसी पीडीएफ फाइल चेक करना पड़ेगा. इट इज योर सी एक्सआरडी विल गिव यू जस्ट दीज पीक्स. सो फर्स्टली यू नीड टू सी थीटा देखेंगे, फिर देखेंगे आपके पास सातों क्रिस्टल स्ट्रक्चर हैं, 14 ब्रोवेस लैटिसेस हैं, उन सबको फाइल को चेक करना है. लेकिन आसान क्या है, जैसे मान लीजिए आई एम टेकिंग आयरन एंड ऑक्सीजन, आयरन ऑक्सीजन ले रहा हूँ. सो आई नो दिस इज आयरन ऑक्सीजन, सो इट्स ऑक्साइड. So tentative, let me see, this will give you tentative cubic structure. So I will check with cubic. मान ली cubic नहीं मिल रहा है, तो then I'll see whether orthorhombic is getting form or not, or tetragonal is not getting form. So I have to check. It's not like मैं assume करके चलूँगा. It is not the case. So I am fortunate. It is the last slide. I am very fortunate to have my mentors like Sri Prasad, and sir also has same mentor. So that way we never met, but I mean he's very much senior to me. So he's very very senior to me. But I have also worked with Professor Jangjam Hoon and Professor Namjang Kaur. So and following are my PhD students. I have not mentioned these young PhD students right now. Maybe in the later slides I will mention them. I have students like Ritu and Shruti right now sitting here. And Sarvesh is also, I think Sarvesh is mentioned, yes, he's mentioned. Rizwan, we have a Rizwan right now. Although he's working in the institute, but not at our role. He is a technical staff with one instrument, but he has helped me a lot. Rizwan, he had been with me since the starting of that center. So we have established the center with his help, और तब से हम लोग बना ही रहे हैं. So I think, thank you all. Sir, shall I बंद कर दें? I think sir will. Sir, I will come.
So, until when you want to sit here? What time you want to finish? Huh? 5:15, 5:30? Okay, or you want to leave? 5? Okay. Okay, we have 35 minutes, so let me try to speed up. Okay, first I will start with the recap of what you learned in the morning. So, in the morning I introduced magnetic field, how we can generate magnetic field, what are the uses of magnetic field and so on. So, I introduced 3 concepts. One is by sending current through wires, this is what Oersted find out. Then we can create solenoid, use solenoid to create magnetic field. Then we can also use electromagnets, where you insert a ferromagnetic core inside the solenoid, which enhances the magnetic field by an amount which is related to the relative permeability. Okay. So, for typical soft magnetic materials, the mu r or relative permeability can be like 100, 140. So, you can enhance the magnetic field by a ferromagnetic core. So, that is the first concept we learned this morning. Then secondly, I told you that even though the common man call magnetic or non-magnetic only 2 types of materials, in physics we have 5 different terms for different kind of magnetic material property. Okay, so, we have diamagnetic material, paramagnetic material, antiferromagnetic material, ferrimagnetic material and ferromagnetic material. Okay. So, these 2 are these 3 you can call them ordered magnetic materials, ordered because their spins are either parallel or anti-parallel. So, there is some sort of ordering. So, we call these 3 as ordered magnetic materials. Paramagnetism, there is no order, the spins are random, and in diamagnetic material there is no uncompensated spin. Okay. So, they are different class of materials. Then I started with the concept of magnetic moment. Magnetic moment is the tiniest magnetic dipole. Okay. So, if you take the spin of an electron, the spin of electron you can imagine as a very tiny magnet. So, that is the fundamental magnetic moment. So, it is expressed by Bohr magneton. So, I also gave you the number corresponding to Bohr magneton. How much, what is the value of Bohr magneton I gave you this morning. So, this is the fundamental magnetic moment. So, this magnetic moment can come from orbital motion, because when electrons go around nucleus they generate a magnetic field, that is orbital magnetic moment. But in the magnetic materials we are interested in, iron, cobalt, nickel, the orbital contribution is negligible. Then electron spin also is like a tiny magnet. Okay, so, electron spin we can say that is one reason for magnetic properties. Okay, but that is not fully true. All the atoms have electrons, all the electrons have spin. So, spin alone is not responsible for magnetic properties, it is the uncompensated spin. So, how many spins are matched or unmatched. So, I give you the example of iron. So, in the iron atom, in the D shell we have 5 up spins and 1 down spin. That means there are 4 uncompensated spins. Okay. So, these 4 uncompensated spins give rise to 4 Bohr magneton per atom in the case of iron. So, in a similar sense, cobalt has 3 Bohr magneton per atom, nickel has 2 Bohr magneton per atom and so on. But again this alone is not responsible for magnetism. So, if you take the same logic, chromium has 5 Bohr magneton per atom, manganese has 5 Bohr magneton per atom. So, this alone is not enough. Then I introduced the concept of exchange integral. So, Heisenberg he introduced that The exchange integral is the one that determines whether the neighboring spins are parallel or anti-parallel. Okay. So, he came up with this formula. So, spins are vectors, so they have certain direction, they are angular momentum is a vector. So, if there are two spins S1 and S2 next to each other, you take the dot product, and dot product multiply, that dot product is a scalar. So, J is a scalar. So, you multiply these two, then you get some energy. So, this energy has to be minimized for any system. Okay. So, in the case of antiferromagnetic materials, this J is negative. So, if J is negative, this term will be positive, and the energy will be minimum when S1 and S2 are antiparallel. Okay. And in the case of ferrimagnetic material, also it is the same criteria as the antiferromagnetic material, but the two spins are of different magnitude. So, S1 can be larger than S2 or S2 can be larger than S1, but S1 is not equal to S2, the magnitude is not the same in the case of ferrimagnetic materials. And for ferromagnetic materials, J is positive. So, if J is positive, energy will be minimum when S1 and S2 are parallel. Okay. So, because of this reason, we can say that ferromagnetic materials have parallel spins, antiferromagnetic materials have antiparallel spins, and ferrimagnetic materials have antiparallel spins, but of different magnitude. Okay. So, that is something we learnt. Then how do we measure magnetic properties? How do we find out whether a material is ferromagnetic or diamagnetic? So, for that I introduced the concept of VSM, vibrating sample magnetometer. So, I told you that this VSM operates on the basis of Faraday's law. That means, if there is a change in magnetic flux, there will be a voltage produced in the pickup coil. So, we can use this voltage to find out the magnetic properties. Okay. So, based on VSM, we can measure MH curves. So, if you measure the MH curve of paramagnetic materials, it will be a straight line. So, if you increase H, M will go like this. If you decrease H, M will go along the same path, along a straight line. So, the slope is what we call susceptibility. So, susceptibility is the slope of this line. Okay. So, slope will be positive for paramagnetic material, negative for diamagnetic material, and we can also do the temperature dependent susceptibility. So, based on the temperature dependent susceptibility, we can distinguish between these three types of magnetic material. Okay. And if you measure the MH curve of ferri or ferromagnetic material, you will not get a straight line, you will get a complicated shape like this. So, we call this as hysteresis loop. Okay. So, I asked you to visualize the saturation magnetization point, remnant magnetization point, and coercivity. So, these are some concepts that we learnt, and later we learnt about the two types of ferromagnetic materials. So, I introduced that there are hard magnetic materials and there are soft magnetic materials. So, hard magnetic materials have a large coercivity, they have a large remanence, and the soft magnetic materials have low coercivity, and they do not have a large remanence. And I also told you that this difference come about because of a property called anisotropy. Okay. Anisotropy is basically you try to measure the property of a material in different direction. If the property you measure is different in different direction, we say that the material is anisotropic. Okay. So, you may find that there is low remanence in one direction, and you to saturate the magnetization you need large magnetic field, then you call it hard direction, and if you can easily increase the magnetization as a function of field, then we call it easy direction. So, I gave you some analogy to remember which is the easy, hard direction and so on. Okay, then later I introduced 3 types of anisotropy. First one is magnetocrystalline anisotropy. So, if you take cobalt crystal, for example, cobalt is hexagonal. So, in the case of cobalt crystal, this is the C axis. So, the easy axis is in the C axis direction, and the A, B planes are hard direction. Okay, anything is hard direction. It is easy to magnetize, and the magnetization is always in the easy direction. So, if you take the cobalt atom, all the cobalt atoms will have their spins pointing in this direction, or in the opposite direction, any of them are okay. So, it has to be parallel or anti-parallel. So, 2 easy directions. Okay, so it can be in this direction or in the opposite direction. And the second anisotropy I introduced is shape anisotropy. So, in the case of shape anisotropy, depending on the shape, for example, in the paper, if you try to magnetize along this direction, north south poles will be closer to each other. So, this is a hard direction, whereas anywhere here are easy direction. Then the third term I introduced is interface anisotropy. Basically, if you have a thick cobalt film, then the magnetization will be lying in plane. However, if you break the cobalt to be very thin, you make multi layers of cobalt, platinum, and so on. So, you break the interface, you create some structure like this, then you can make the magnetization point in the perpendicular direction. So, that is one example of interface anisotropy. Then the second example is like if you place a ferromagnetic layer with the antiferromagnetic layer, you can shift the hysteresis loop along one direction. So, that is another type of anisotropy. Okay, then the last concept that I introduced in the morning is to do with domains. So, we learned that in ferromagnetic materials the spin have to be parallel, but if too many spins are parallel, then there is going to be a large magnetostatic energy or demagnetizing energy. So, people use any of these two terms, magnetostatic energy or demagnetizing energy. So, basically this energy is like trying to keep two magnets with the north poles up next to each other. So, there is a very large energy trying to push them. But if you keep the north pole and south pole and south pole and north pole next to each other, you minimize the energy. The magnets stick to each other and you minimize the energy, right. So, similar thing happens. So, when you have too many parallel spins, the system may or may not form domains. Okay. So, what happens if you form domains, you minimize the magnetostatic energy, but you create domain walls, and in the domain walls there is some energy. So, you increase the domain wall energy. Okay. So, ultimately whether the system forms magnetic domains or not depends on which one will reduce the overall energy. For example, if you reduce the magnetostatic energy more than the energy you need for forming domain wall, then domains will form. So, this is like you do not mind losing 100 rupees, but you gain 1000 rupees, right. Then you do not mind doing that. So, in this case domains will form. However, if you try to reduce magnetostatic energy, but in that process you need to spend more energy for domain wall, then the domains will not form. Okay. So, that is like losing 1000 rupees to gain 100 rupees, you will not do that, right. So, which one is large? Ultimately, which one leads to a reduction of overall energy, that will determine whether system will form domain or not. So, in the case of magnetism. If the objects are very large usually, then there will be multi domains like this, but if the objects are small, then they will be in single domain, they may not form any domain. So, within this 50 nanometer, the system won't form 2 or 4 domains, because there will be more energy to be spent. So, within 50 nanometer, there are only fewer spins, right? You have a limited volume, so limited atoms. So, there are not too many parallel spins. Okay, the energy, magnetostatic energy is not going to be high. So, there is no need to form domains, whereas when the size of an object is very big, then you have too many parallel spins and you have too large magnetostatic energy. So, the system will form domains and minimize the energy. Okay. Okay, this is all you learned in the morning. Okay, now we are coming to the last aspect of the magnetism. Let us say this is a piece of magnetic material. Okay, I bring a magnet next to it. So, there are few possibilities. Okay, so this is a magnetic material and I bring a magnet next to it. So, one possibility is that the region only near this magnet get magnetized. Okay, the rest is not affected by magnet. That is one possibility. The second possibility is even though my magnet is small, my magnet affects a large region. Okay. So, imagine you have a pen and a paper. So, in one case this pen is writing only in a area which is determined by the tip of the paper, the tip of the pen, and in another case maybe you have a paper that bloats like a filter paper and you use a ink pen, you try to write, the ink spreads, right. So, two possibilities can happen. So, in a similar sense, which one do you think it is possible? So, I have a magnet, in one case only this region gets affected, in another case a large region gets affected. So, which you think is possible? Maybe raise hand. One is possible, two is not possible, two is possible, one is not possible. Option 3 is both are possible, it depends. So, who wants to vote for one? I mean, I bring a magnet, the magnet only magnetizes the region directly below the magnet. So, that is scenario 1. Scenario 2 is like the magnet magnetizes a large region, much larger than the magnet itself. Which you think will happen? One or two or three? 2. Okay. How many say 1? Okay, a few hands for 1, a few hands for 2. How many of you raise hand for 3? Okay, the correct answer is 3. Okay, both can happen. It depends on the circumstances. Okay, so I gave you the example of the paper, right? So let's say I have an ink pen. I have an ink pen. If the paper is as good as this paper, then the line I draw will be very sharp. Okay, but if the paper is like the filter paper you use in the chemistry lab, I use ink pen, try to draw, then the ink will spread. Okay. So, in a similar sense, depending on the paper, I can get sharp line or wide line. So, similarly, in here, depending on how I prepare my magnetic material, I can have scenario 1 or scenario 2. Okay. Suppose I do sputtering and I create a thin film. Okay. I haven't done any special preparation. So, in this case, I have certain film A. Okay, I do sputtering, I do some special preparation. Okay, I will teach you what is this special preparation. Then I get film B. Okay. So, typically most of the people do this. Okay. So, when they grow sputtering, they do not do the special preparation, which I am going to talk about later tomorrow. So, when you prepare magnetic films like this, okay, then you encounter your films will have form domain. Okay. The film you prepare, or most of the magnetic materials people normally prepare, have this property that there are domains. Okay. Okay. So, film A or most common materials that people prepare have multi domains. Okay. So, when you have a film or material with multi domains, then the magnetization, I mean how this magnet will affect this material, that is what we call magnetization reversal mechanism. I mean how this magnetic material respond to this magnet is what we call magnetization reversal mechanism. So, that will be via domain wall motion. Okay. So, I will explain what domain wall motion is. For example, here you see we have four domains. So, one domain magnetization is pointing towards the right, another one magnetization is pointing down, magnetization is pointing left, magnetization is pointing up. We have 4 domains, and if I apply a magnetic field along this direction, up direction, you see that the up domain expands, all the other domains contract in size, and this is like this wall which was here has moved from here to here. Okay. Similarly, this wall was here and it has moved from here to here. Okay. And if you apply more magnetic field, this domain will expand further, all the domains will be gone. Okay. Finally, this whole object will have magnetization in the direction of magnetic field. So, one domain expands by the motion of its wall. So, this kind of reversal mechanism is called domain wall motion. Okay. So, here is the video that we captured in our lab. So, this is a film with perpendicular magnetic anisotropy. So, you can assume that black means north pole is towards you, gray means south pole is facing towards you. Okay. So, when we apply certain magnetic field, you can see the black regions expand. Okay. So, the boundary between the black and the gray region is a domain wall. So, this is one domain, and you can see that this boundary is a domain wall, and you will see that it expands. So, you see. So, the domain wall moves and finally the whole film has black region, which means all the magnetization is now in the north direction. So initially you had south polarity dominant, now domain walls have moved and you see the all become north. Okay. So this kind of reversal motion is called domain wall motion. And another type of reversal motion, mechanism that I want to discuss today is coherent rotation reversal of magnetization reversal. Okay. So I told you that if you don't do any special preparation, you will end up with having a film where there are multi domains. Okay. But if you have this special preparation, there is a secret recipe I will tell you tomorrow. Okay. With this secret recipe, you will prepare a film B where you will have single domains. Okay. So you will have single domains inside the film. So when you have single domains, there is no domain wall motion. So domain wall motion happens only when there are multi domains. Okay. When you have single domains, what happens is when, let us say, initially the magnetization of these single domains are going into the board. Now I apply magnetic field coming towards you, then maybe this film reverse first, this grain reverse first, and after some time this reverses, and later this reverses the magnetization. So from going into the board, now the magnetization is pointing towards you. Okay. Then this reverses and so on. Okay. So all the tiny regions, they reverse their magnetization independent of each other. Okay. Here one region reverses first and the reversal spreads, right. So this is like the filter paper. So in the filter paper, you keep your pen, the ink spreads, right. So that kind of motion happens in domain wall motion. On the other hand, in the case of coherent rotation, when your film has single domains, all the single domains will reverse independent of each other. Okay. So this kind of reversal mechanism was proposed by, the theory was proposed by these two scientists, Stoner and Wohlfarth. So we call it Stoner-Wohlfarth reversal mechanism, or people also use the word coherent rotation, uniform rotation, and so on. So what is the meaning of coherent rotation or uniform motion is that, so we have one single domain. So within that single domain there are several spins. Okay. So when you apply a magnetic field, all these spins will rotate together. And for example, initially let us say all the spins are pointing like this. Okay, now you apply a magnetic field along this direction. So this is within one single domain. Okay, I draw many circles, right. So within this circle there are many spins pointing up. Now you apply magnetic field in the opposite direction. So they will all go together in the same direction. Okay. At another instance, maybe they are like this. After some time, they will be like this. Then finally, they will reverse to the other direction. So coherent means what? In phase. Okay, they they are going together in the same way. if this pin tilts by 15 degree, this also tilts by 15 degree, and so on. Okay. So all the spins reverse together, and that's called uniform rotation or coherent rotation. Okay, so this kind of reversal mechanism is called Stoner-Wohlforth reversal mechanism. And in this case, your hysteresis loop in the easy direction will look like this. Suppose you have, let's say I take only one domain, okay, just one particle. You can say this is one particle, and I apply, initially it was magnetized like this. I apply magnetic field in the opposite direction. So this particle will reverse at a field called HK, anisotropy field. So this anisotropy field is given by 2 Ku over Ms, where Ms is a saturation magnetization, which you learned before. Ku is called anisotropy constant, which I will elaborate later, but right now just you remember that this Hk depends on Ku and Ms. This is proportional to Ku, inversely proportional to Ms, and this will determine where the reversal happens. Okay. So in the easy direction, hysteresis loop will look like this, and in the hard direction, the magnetization will increase gradually, and at Hk, at this value, the magnetization will saturate. Okay. So this is the easy axis loop of Stoner-Wohlforth model, and this is the hard axis loop, and this Hk is defined by 2 Ku over Ms. So this one I will discuss later, but today I just want to show. I told you, right, if you do some special preparation, you can have these kind of single domain particles like here. Okay, so this is one single domain particle, another single domain particle, and so on. So when you do hysteresis loop of this special sample film B, then you will notice that these tiny regions, they switch their magnetization independent of each other. So you will notice that some switch first, some switch later. Okay, not all of them switch together. Okay, so you see some switch first, some are still red. Okay, all became blue. Now when you go in the other direction, only 2 became red, a few more became red, a few more became red, finally all became red. Okay, so here there is no spread of domains. Okay, so in the domain wall motion, in this particular case, you saw that there was a domain and the domain expanded, but here you have tiny regions, they switch independent of each other. Okay, so this mechanism is called coherent rotation or Stoner-Wohlforth reversal mechanism. Okay, just I will play this video and end on time. Okay, so here I am showing how the hysteresis loop property will be different when you have Stoner-Wohlforth reversal mechanism. So imagine that there are 16 or some grains. Okay, there are 7 grains. So initially all have same magnetization, and when you go towards the negative field, some reverse first, some reverse later, a few more reverse later, and finally all reverse. So again, when you go from here to the other side, one reverses first, a few more reverses, a few more regions reverse, and finally all regions reverse. Okay, so this is how the hysteresis loop is obtained in the case of Stoner-Wohlforth reversal or coherent rotation mechanism. Okay, so there are some questions which we will do tomorrow, and with that we end today. Thank you. So I am on time. Okay, exactly 5. Okay, see you tomorrow. Thank you.